So the next talk is by Ziyuan Feng. He's a PhD student at the University of Shanghai, Jiaotong. And he will talk about his work, TensorIR, an abstraction for automatic tensorized program optimization.
Hi everyone, I'm a student from Shanghai Jiaotong University, and I'm excited to share our new work, TensorIR, an abstraction for tensorized program optimization. Let's start with the motivation. Deploying models on various devices has become an important topic. The wave of hardware specializations bring a diverse set of acceleration primitives for multi-dimensional tensor computations. These new accelerator primitives, along with the emerging machine learning models, bring tremendous engineering challenges to us. To deploy models on tensor hardware, we need to write Tensorized program, contain tensor instructions to compute a part of tensor rather than a scalar. Usually, Tensorized program has the following essential parts. The first one is optimize the loop nesting with thread binding if we want to run it on our GPU. And second, we need a multi-dimensional data load and store into specialized memory buffers. And last is the most important one. We have the opaque tensorized computation body, which is also the major challenge for automatic optimization. Because those instructions are opaque, the compiler does not know the instruction will read or write how much data from memory and does not know the instruction to do what computation like. To solve that problem, we introduced the TensorIR abstraction, a new abstraction designed for tensorized programs. Block is the most important abstractions in TensorIR. Let's start with a simple scalar program. As we can see in this program, we have added 2 blocks here, which warps the innermost computational body. We take a further step and transform the previous programs a bit. Please take a look at the block B in this program. It is a vectorized, or we call tensorized block now, which computes 8 elements at the same time. Notably, we explicitly mark the read-write region to this block. That information will make the block transparent from outside of the view, even though the block body is opaque. As block is a basic unit of TensorIR, it can represent tensorized computation natively. So we can say that we treat the tensorized computation as a first-class citizen in TensorIR. Now let's look at the definition of the block. There are several parts of the block. The first one is the outside loop nesting. Please note that the loop nesting is not a definition inside the block. However, it's very important for tensorized program and block abstractions. So we also listed it here. The second one is the iterators with iteration kind and its domain. Taking these MATMOD programs as an example, we have 2 spatial axes for n and m dimension and 1 reduced axis for k. Also, we can bind the iterator to our expression of outside loop nesting. Then it's the producer and consumer dependency relations, which is also called read-write regions, indicate the data read and write by the block. It can be a subregion of the tensor. In this case, it's a 4x4 subregion for both buffer A, B, and C. With these read-write regions and iterations, the block can be transparent and the compiler knows what kind of data and what the region of the data it can be read or write of the block. And the last one is the computational body. Note that the body can be only indexed by the block iterators, but cannot directly use the outside loop vars. It will bring a following question: why we need such abstractions and why we need such constraints? The answer is that we want to isolate the inner computation from the outside loop nesting. Since all indexes are using the iterators, the iteration binding will be the only way to interact between inside block and outside block. If we want to optimize the outside loop nesting, no need to update the block body, but only to change the binding value of the iterators. And if we want to schedule the body of the block, No need to worry about a complex loop nesting outside the block, but only to replace the block body. Now we have the isolation abilities. Let me introduce the Tensorized step in TensorIR. So TensorIR divides the optimization problem into two separate ways: loop nesting and computation body. When transformation loop nesting, with the help of block isolation, we don't need to care about the internal implementations, no matter the block use Scala-based computation or opaque tensor intrinsic. When considering how to compute the block, we can map the tensorized body into different implementations. In this example, we can take either 4x4 Matmore microkernel and directly Scala computing. We can combine both two operations in any order and finally generalize the program we want. Here is our key ideas. Divide the problem into sub-tensor computation blocks. Generalize loop optimization for tensorized computation, and combine the above approaches in any order. Then, in order to fully make use of the set of improvements, we need an automatic solution to optimize over a set of transformations and map computations to the native tensor instructions. Our system takes an input program from user and tensor intrinsic descriptions about the hardware platform as input. A tensor intrinsic includes two parts. The first one is semantics, which tells the compiler what kind of computation the tensor hardware can do. And the second one is the implementation, showing that they compute on the hardware using the tensor instructions. Then the tensorization part is to match the input program and the semantics of the intrinsic, and try to replace the computation with the intrinsic implementations as a tensorized step. Here we match the program and the intrinsic successfully. Then we tile the program to satisfy the requirements of the intrinsic and create a block, saying it is a tensorized candidate. Next, the auto-scheduler generates program sketch candidates that use the tensorized computation and then decide the program sketches according to the matched result. Notably, here we take a data movement at the first class citizen. Existing auto-scheduler for tensor programs focus on their design on the schedule of computations and treat data movement as the secondary priority. However, since tensor instructions largely implement the throughput of the computation, data movement becomes a bottleneck of the tensor program. Specifically, we insert the autocopy block into the place where the sketch generation rules decide to perform data movement, which can optimize memory operations efficiently and independently. And the last step, for a given search space deduced by the tensorized program sketches, we perform evolutionary research guided by a learning-based cost model to explore the search space and find optimized tensor programs. So let's see the experiment results here. This slide shows the performance on NVIDIA GPUs. Comparison to the existing machine learning compilers, TensorIR brings up to 7.5x speed up across workloads. Combination to the platform-specific libraries, we pick Catalyst and TensorRT, which are regarded as the fastest libraries for GPU with tensor cores. We achieved some speed up on part of the workloads, while the TensorIR can still get close to or match the existing vendor-specific solutions on the other workloads. In all cases, these baselines are optimized by dedicated engineering teams, while TensorIR enables automatic compilations with only the input program and the given tensor intrinsics. Here is the end-to-end model evaluations on NVIDIA GPU. TensorIR significantly outperforms existing machine learning compiler solutions and achieves similar or better throughput on popular networks compared with the inference libraries on GPUs. Still note that these models are standard models on MLPerf, which means NVIDIA engineering team takes large effort on it, and it is the strongest baseline for GPU with tensor cores, I think. Here is another experiment on ARM CPU. The last two slides evaluate TensorIR on NVIDIA GPUs. In this slide, we study how it's easy to generalize TensorIR to different platforms. We evaluated the results on ARM's platform with provided the description of intrinsic with 8-bit integer dot. We call it also S dot. We get the same level of performance as heavily optimized platform-specific libraries, ACL, on ARM CPU, and outperforms them PyTorch and TVM on end-to-end evaluations. As a summary, we introduced the block abstraction, which separates the tensorized computation from the loop transformations, and the same abstraction to unify to represent the tensor intrinsics with hardware semantics and hardware implementations. Third, a new tensorized aware automatic scheduler to usualize the hardware and achieve the similar or better performance than vendors provided libraries. That's all, thanks.